So today we shall have two speakers. I guess Professor Krajewska Radzewicz is the first one, and then will be Professor Krajewska. They are both related to the this year Nobel Prize in Physics. You see it here. And both are actively working in the field. So hopefully we shall learn with all details what was it about this prize. Thank you so much. Please don't forget to sign the book.
Good afternoon, everybody. Let me start with thanking the organizers for inviting Katarzyna and me to this lecture. It's a pleasure to be here and talk to the distinguished audience, which I'm sure will appreciate what we have to tell you today. We'll be talking about the Nobel Prize 2018 in physics. You probably know for what the Nobel Prize was awarded. Still, let me just for clarity remind you that the prize was awarded for groundbreaking achievements in the field of laser physics. Actually, the prize was divided into two parts. One part went to Arthur Ashkin for the optical tweezers and their applications to biological systems, while the other part went to a couple of people, Gerard Moreau and Donna Strickland, for their method of generating high-intensity, ultra-short optical pulses. Ashkin is an American, Moreau is a Frenchman, and Strickland is a Canadian. So the two parts are not well connected. And talking about both in the same lecture would be quite difficult. So we decided that we'll tell you only about the second part of the prize, leaving the first one without comment. So we'll be talking only about the method for generating high-intensity, ultra-short optical pulses. Generating intense laser pulses was and still is a very, very interesting field of research and technology. There were numerous attempts to build lasers with high powers or high pulse energy. Probably the most spectacular of such projects was what is called National Ignition Facility, which was commissioned in the USA and completed about 10 years ago. The idea was to ignite nuclear fusion reaction using laser beams. The facility itself went through several stages. The picture you can see on the right bottom shows the last stage of the facility. The laser system delivers about 200 laser beams. In those 200 beams, you have about 4 megajoules of energy. And if you account for a pulse which is nanosecond duration, then you end up with something like 500 terawatt peak power. To give you some idea, if it's a large amount of power, if it's a big power or small power, let me tell you that all electrical plants on the Earth amount to several terawatt power. So during this very short time, which is nanosecond in this case, the power exceeded the electrical power by orders of magnitude. Now it turned out that even with this huge energy and huge power, the nuclear fusion did not work. The project failed, and the facility is used for other purposes right now. If one imagines how much it has costed, then it's easy to understand that there will be no other facility like that, because no politician will be willing to put so much money to build a machine which might or might not work. we cannot really hope that the future will have facilities like that. And if you want to pursue high intensity laser physics, we have to find some other way. Luckily, there is a way to do that, and this is connected with the fact that we can use very short laser pulses. And if you have a short laser pulse, then you, by definition, end up with a very broad band, many frequencies within the pulse. If you have this broad band, then you can play tricks with that. But first, let me tell you about the simple idea which lies behind this, the second part of this year's Nobel Prize. And this is the formula you see here. If you have limited energy available in our laser pulse, then we can play tricks for the peak intensity or peak power by simply making the pulse shorter and shorter. And people realized that fact a long time ago in the early 70s. They have started building amplifiers to amplify femtosecond laser pulses. And it turned out that it is a difficult task. And it is difficult because nature is not linear, which means that the response of the media to laser light is not linear. In particular, we have what is called nonlinear refractive index, which means that the index of refraction is a function of laser intensity. And this leads to several effects which are not good for laser amplifiers. One of them is self-phase modulation, which means that upon propagation through the amplifier, the pulse achieves a nonlinear phase which cannot be compensated afterwards. And that means that the output pulse is long and it has very rich structure. And it's quite useless as such. But then you have also the self-focusing. And self-focusing means that if the power is strong enough, even a plane wave can start focusing within a medium. And if you allow it to do that, you will end up with burning something inside your amplifier. Simply because the intensity of light in the medium, in the focus of the beam, will be very strong. So, what can we do? Well, I started telling you about the bandwidth of very short pulses. And the idea, which has been used by Moreau and Strickland, was to somehow stretch those pulses. And we can do that because if you look at the numerical example shown here, for 10 femtosecond pulse, you have the spectrum which covers the whole visible and part of the infrared, which means you have really broad spectrum. And then if you can build up a device which will chirp the pulse, you can extend it in time. You can stretch it simply by delaying some of the frequencies with respect to the other, and you end up with either up chirp with low frequencies coming first, or a down chirped pulse with high frequencies coming first. So the trick is here. Trick is here. You have somehow to be able to chirp the pulse. Going back to the idea of Strickland and Moreau, they have put up an idea, and they actually showed that the idea is valid by doing the experiment for the following system. They started with a short laser pulse, put it through a pulse stretcher, which stretched it in time. Then they amplified the pulse in the laser amplifier, and at the very end, the pulse was compressed back to almost initial duration. This way, you can have both. You can have short pulse, and you can have low intensity in the amplifier, so you don't damage your amplifier. Because if you do, then it's not a good amplifier anymore. So that was the basic idea. Please pay attention to the paper, to the journal they published the paper in. Impact factor is not that relevant after all. It means something to us, but not necessarily to the Nobel Committee, which awards the prize for the achievements, not for the impact factor of your publications. At the time of their work in the middle 80s of 19th century, people already knew about systems that allow to compress the pulse. And this is called diffraction grating pulse compressor, invented in 1969 by Tracy, which consists of two identical diffraction gratings. We come in with a short laser pulse. We spread the spectrum angularly here, and then the second diffraction gratings directs the different frequency components towards flat mirror, which reflects the beam back, and we can pick it up here as a single beam. Apparently, different components of the spectrum travel different paths, and this way we can actually do something with the duration of a broadband pulse. For example, we can do the following. We can take a uptripped pulse, a long uptripped pulse, and compress it, as indicated here. I come in with a long uptripped pulse, and I end up with a pulse that is shorter in time, with all the frequency components more or less coming at the same time at the output. The problem which faced Moreau and Strickland was that they didn't know how to stretch the pulses, and from what I understand, it was Strickland's idea to use a long stretch of single mode fiber to actually stretch the pulses. So the actual system they have used is shown here. We have a source of short laser pulses, then the stretcher is 1.4 kilometers of single mode fiber, then they go into an amplifier, standard regenerative amplifier, and then compressor, which compresses the pulse to the initial duration. All right, this is not a very universal system because the properties of the stretcher and compressor do not match very well. And in particular, for very short pulses, they have used picosecond pulses. For femtosecond pulses, this mismatch between the properties of a stretcher and compressor will affect the output pulse. It will be longer than expected. So another way of stretching optical pulses was required, and this has been proposed 2 years later by Martinez, who proposed what we call diffraction grating stretcher. And again, we have two identical diffraction gratings. The beam is coming here, it's spread on the first grating, and then there are two lenses sitting in between the gratings and the flat mirror, which reflects the light back. And if you look here now, is the opposite to the compressor because the high frequency components have longer path. So which means we end up with a uptripped pulse, which is required for the compressor. The actual system, it's not as simple as I show here. I will show an example of a stretcher we have designed for one of our systems, which is based on the Offner doublet. And actually, you never use gratings here because they introduce a lot of distortions into the system. You use two mirrors, one which is concave and the other which is convex, and then a single grating suffices to build the whole system. And then to see it's not so easy to build in the line. All right. So after the initial developments and during the 80s and 90s, there was something there was the development of what I call the CPA standard, Tripped Pulse Amplifier Standard, which basically contains all the components I have mentioned before, which means we need a seed laser, a source of short pulses. Femtosecond oscillators deliver pulses with rather small energy in the range of picojoules up to millijoules, up to nanojoules. So they are relatively small energies. And if you want to build something stronger, then you have to go through the amplifier. And this is a typical system. You use the stretcher. Then you go into the optical amplifier, and then you compress the pulse to end up with something that is significant. Currently, there are quite a few commercial systems based on this design. They are mostly used for research in femtochemistry, in physics, and other areas. What is worth mentioning is the change for the optical amplifier technology. For the last 10 years, people more and more often use optical parametric amplification. And this is a nonlinear process in which you have two beams interacting in a transparent crystal. The interaction is such that it takes the power from the pump beam, which is a strong short wavelength beam, and puts it into the amplified beam, which is longer wavelength, a femtosecond pulse. The advantage of using optical parametric amplifier is that you don't have basically any thermal effects in the crystal. In the laser amplifier, you have to store energy, and usually there is some heat generated in the process because you don't extract all the energy in radiative processes. You deposit some heat. And the heating, especially large cross-section amplifiers, is difficult because then you cannot really cool it down very effectively. You have to wait for like an hour for another shot. It's not very convenient to do the experiments with a shot per hour, because it's difficult to collect statistics then. So the advantage of using PCA is such that you don't deposit any energy into the crystal, there's no heating, and you can build repetitive systems. For example, you can have a system that you run at 10 Hertz. And at 10 Hertz, you can collect some data in a finite time period. All right. I will end up with this graph. And Katarzyna will start with this graph, showing what was happening in the field of extreme high-intensity lasers for the last, 60 years, 70 years? As you see, the vertical scale varies from 10 to 10 up to 10 to 30 watts per centimeter square. Currently, we are somewhere here. We are somewhere here. This is not operating yet. This is not operating yet. There are delays there. But look at the numbers here, and look what happened in mid-80s of 19th century. There was this long period of basically no increase in the available peak power until Moreau and Strickland came and told us, do it this way. This is the right way to do it. And the CPA changed everything, because since then, there is a constant growth in the available peak power, and we end up with what we call relativistic optics, or maybe ultra-relativistic optics, and Katarzyna will tell about that much more. The current record belongs to the Chinese system. It's 5 petawatt, and there are plans to build stronger systems. One of them is ELI, which was invented and proposed by Moreau. This is a European laboratory, pan-European laboratory, in which we have 2 lasers, 10 petawatts each. The Chinese plan to go to 100 petawatts. And Russians proposed even stronger system, but nobody knows if there will be funding for that, and if there will be, and when they'll be completed. This is not really, those are not very serious proposals as yet. But the early system is the building's already there, and they are putting the machine inside the building, so it should be operating in some reasonable time. And I'd like to stop here and. Let Katarzyna tell you about the applications of this technology.
Good afternoon, everyone. So basically, I will start with discussing this graph a little bit more. It shows how the laser field intensity, the peak laser field intensity, has increased since 1960, which is the year when the laser was invented. So today, we are where I put this white spot, actually. So it's slightly more than 10 to the 22nd volts per centimeter squared. And Professor Radzewicz said, we are there because of the CPA, among others achievements. So anyway, while we are increasing the laser field intensity, we are actually passing through different regimes of laser-matter interaction. So let me give you an idea what is happening when we do that. So the laser field is basically propagating electromagnetic wave. So actually, when we have a charged particle interacting with such a wave, we can just, let's think about it classically. So basically, the Lorentz force tells you how such a particle interacts with the laser field. And if we are in the non-relativistic regime, why do I have this? Okay, sorry about that. So once we are talking about non-relativistic regime of laser-matter interaction, then basically particles are moving with rather small velocities, meaning that actually what is determining the dynamics of the particle in such a field is basically the E component of the Lorentz force. So what particle is doing, it's actually oscillating along the E field direction. Let's say this is linearly polarized field, so it will be oscillating like that. If we, however, go to relativistic regime of laser-matter interaction, so the velocities are much larger, then actually the magnetic component of the Lorentz force also plays a big role. So the dynamics of the particle is changed. Except of small oscillations, it actually kicked basically in the direction of the laser field propagation. So this is the key difference, which also leads to very different physics there. So after the CPA was invented, we basically were able to address the physics of bound electrons. So the laser field was such that it actually did make a difference on bound electrons, meaning that the corresponding E field was comparable to the electric field that bounds the atoms. So this actually would correspond to the intensity roughly of the order of 10 to the 16 volts per centimeter squared. If we increase in the intensity even larger, then the work done by the E field over just the laser wavelength is comparable to the rest energy of the electron, and it means that the electron starts to be relativistic in such fields, and this is more or less happening when the intensity is roughly 10 to the 18 volts per centimeter squared. If we would able to increase the intensity even higher, we would be able to make protons relativistic. So this would be happening at roughly 10 to the 24 volts per centimeter squared. And finally, we would be able to hit what is known the Schwinger limit. Actually, I prefer to call it the Zoiter-Schwinger limit. So this was actually derived for the static electric field, and it tells you that the work done by the electric field over the Compton wavelength is comparable to mc squared. And this also means that the electric field is able to break the vacuum. And if you translate this E field into the respective intensity, it would be approximately 10 to the 29 volts per centimeter squared. And I'm talking here about numbers for the optical lasers because this Nobel Prize was given actually for the development of optical lasers. So now I want to tell you why the CPA was so important, and let me start with the example, which concerns bound electrons. So the most important process which which I want to talk about, is what is known as high-order harmonic generation. And this is the process when the atom or molecule interacts with the laser field, and as the result of this interaction, the very short burst of radiation is emitted. And the way it's happening is such that we have the bound atom, the electron bound in the Coulomb potential, and then when the laser field comes, it tilts the Coulomb potential such that the electron can already tunnel through it. So the electron is basically ionized, and then it accelerates in the laser field, so it picks up energy from the laser field. And when the laser field is changing its direction, basically the force acting on this electron is reversed in sign, such that the electron comes back to the atomic core and it recombines. And during this recombination, it emits this short burst of radiation. Typically, it's happening such that those bursts of radiation last for roughly attoseconds. So 10 to minus 18 of the second, very short. And if you would like to look at the frequency spectrum of those attosecond pulses, it would contain the whole range of frequencies, starting with the driving laser frequency up to more or less what is known as the cutoff frequency. And this cutoff frequency actually is determined by a very simple formula where we have bounding energy of the atom plus more or less UP. UP, it's called the ponderomotive energy, and it's given by this formula. This is basically the average energy of electron oscillations in the laser field. So in other words, it's proportional to the intensity, to the peak intensity of the laser field, and inversely proportional to the frequency squared of the laser field. So in other words, this range of frequencies is basically determined by the driving laser field. And the interesting thing is that, of course, if we have those attosecond pulses, one can try to even think about generating shorter pulses. And this, of course, would mean that we need to increase the bandwidth of the attosecond of the pulse, so we need to increase the range of these frequencies, which we are talking here about. And if we know that this cutoff is determined by the parameters of the driving laser field in such a way, one may naively think that it's enough to increase intensity or the wavelength of the driving laser field, and we would be able to go to even zeptosecond pulses. But this is not the way to do it, and I will refer to this later on. But anyway, the high-order harmonic generation, it became a route to actually generate attosecond pulses, and since, I don't know, 2001, when the first attosecond pulse was actually produced until now, so this is like more or less for 15 years, there's this whole new field which is called attoscience that has developed based to the CPA technique. And it actually allows us to understand, control, and image ultra-fast electronic processes. So electronic processes which occur in atoms, molecules, in solid state, and so on. So for instance, we are able to look at chemical reactions or other atomic scale transformations as they occur. So this is a very neat tool to get insight into what is happening in a microworld. But this was the example regarding this non-relativistic regime of laser-matter interaction. When it comes to relativistic regime, the current Guinness record for the peak intensity is 2 times 10 to the 22nd volts per centimeter squared. This record belongs to the Hercules laser, which is at the University of Michigan. At the time where this record was recorded, actually, Gerard Mourou was the lead person of this Hercules lab. So this is the record, but let's look at more typical parameters that are achievable. So let's think about 1 petawatt laser, which is focused up to 10 micrometers, and this gives you intensity, let's say, from 10 to the 20 to 10 to the 22nd watts per centimeter squared. And let's look at the conditions which this intense laser field, this extreme light, can produce in the laser focus. So first of all, you can get very high electric fields in the focus. So those fields actually are by 100 or 1,000 orders of magnitude larger than those that bounce atoms. Then the energies, the ponderomotive energies of the electron in such a laser field, actually they are larger, comparable or larger to the rest mass energy of the electron, so those are huge. If you look at the energy density in the laser focus, this would be of the order of 10 to the 11th joule per centimeter cube. And this is huge. I mean, if you compare it to the solid density, this actually means almost 1 MeV per atom. So this is just a very big number. And also the pressure in the focus is large. It's of the order of gigabars or terabars. So this extreme light delivers very extreme conditions. And now the question is what we can do with them. So one of the examples is actually the laser wake field acceleration, which was theoretically proposed before the CPA was invented, but only shortly after the CPA was introduced by Donna and Gerard. Then it was realized experimentally, and now people really know how to do it very nicely. And the general idea, and I hope I will describe it correctly, is such that you take your petawatt laser and you shoot it in the gas. So basically, you ionize the gas and you produce plasma. And because the ions are much more heavier, then they are basically sitting and they produce this positively charged cavity behind the laser focus, whereas electrons are pushed away by what is called the ponderomotive force. So these are the electrons. However, because of the electrostatic force, they are somehow bunched behind this, what is known as a bubble. And there is basically some effective electric field which is behind the laser focus, which allows people to actually push those electrons with speeds very close to the speed of light. And actually, typically, for this kind of acceleration, you use not that intense lasers, because typically they are like 10 to the 18 or 19 watts per centimeter squared. But the interesting thing is that you can actually accelerate those electrons to 100 MeVs within millimeters. So basically, you get a couple of GeVs within centimeters. And this is how this GeV electron accelerator looks like. As you can see, it's very compact. So this is, of course, there's petawatt laser standing next to it, but I would say it's quite impressive. And another thing that you can use those ultra-intense laser sources is, okay, we learn how to accelerate electrons. We can go even farther and try to accelerate protons or ions. So this laser wake field acceleration doesn't really work very well. So the most brute technique would be just take this laser and just shoot it on the solid target, and then the protons or ions, depending on the target, would just fly away. Of course, there are some techniques being developed because it's not just that simple to get a nice proton beam out of it. And then, of course, what people are talking about is basically to use these petawatt optical lasers to being able to produce very nice proton or ion beams for medical applications. And this is probably many of you knows very well that actually the proton beams are very good for cancer therapy. And they are actually the properties of those proton beams and the way they propagate through the human body and so on are much better than conventional ways of treating the cancer. So actually this proton therapy is particularly good when the tumor is in very sensitive spots such as brain and so on. So actually this is one of very important applications. The other important thing is that once we have this relativistic electrons, you can actually do even more with them. For instance, you can do in all optical setup experiments such that you use the same laser to first accelerate the beam of electrons to relativistic energies and then to scatter it by the same laser beam. In other words, you can do Thomson or Compton scattering, and during this process, you can actually produce very nice X-rays, like in this case, those are X-rays. And I think that this actually is a much better way to get into this, let's say, zeptoscience, because in order to get to this time resolution, we actually have to have MEV photon energies. So if we would be able to take maybe not the electrons which are very relativistic, much more relativistic than just those which come from laser-driven accelerators, and being able to scatter them by a super intense laser field, then we would be able to get to this MEV regime maybe one day. So once we have this nice X-ray beams, we can actually do more. So this is the experiment in which basically the thick uranium disk that was shielded by a steel container was detected by the X-ray source, which was produced from those optical lasers. And this is, of course, very important for security purposes, that without opening, let's say, cargo containers and so on, we can actually look inside of those containers. So, of course, US Army, because this was done by my colleagues from the University of Nebraska in Lincoln, so they do a lot of projects for the US Army, and I think they are doing pretty good with this. So another thing that you can actually do with these high intense laser fields is to do strong field quantum electrodynamics. So this is actually what our theory group is doing, trying to understand strong field QED processes. What we are missing, of course, are experiments. And actually the only experiment, strong field QED experiment that we can refer to is still this very old SLAC experiment. It's already like 20 years old, where they actually saw Compton scattering and also the pair production. But of course, building the super intense laser facilities would actually help us very good with testing our theory. So this is more or less about applications. And trying to convince you that these optical super intense laser pulses are actually have very many nice applications. This map I actually took from the presentation of Gerard Moreau himself, where he shows petawatt lasers in the world, the ones which according to him set the field's horizon. So if he says that, it actually means something. So one of the things I'm happy about is that there is University of Nebraska there, but also I would like to pay your attention to the fact that actually in Europe we have very many petawatt lasers. So I can say that Europe is actually the leader in this petawatt lasers business. And here already on this map there are 3 ELI pillars, which I want to say a few words about, because as Professor Radzewicz said, Gerard is actually the father of this ELI project. So this is extreme light infrastructure. This is huge European project. So basically in 2005, Gerard Moreau got people together at the conference and started to make the case that actually Europe really needs this super intense laser facilities being built, and actually, of course, he made it through. So basically now on the ELI webpage, you can read that father of ELI wins Nobel Prize for laser physics. So I guess they are very proud of him. And ELI actually comprises 4 branches at 4 different locations. Each of them is in different country, actually. So there is attosecond ELI Alps, which is in Hungary. This is attosecond laser facility, so it's devoted to looking at those very tiny, small time resolution problems. There is in Prague, in Czech Republic, there is ELI Beamlines, which actually is devoted to looking at generating very energetic particles and also the secondary radiation sources. There is ELI NP, which is devoted to laser-based nuclear science. This is in Romania. And they want to generate gamma beams and also neutron beams and being able to do some interesting nuclear physics with those. And there is also the 4th location, which is still not decided right now, but this one is supposed to deal with ultra-high field intense science and also with exawatt lasers, if they are possible to be built. So actually, ELI is a place for doing very fundamental physics, very fundamental science, but also it's devoted to all nice applications of those petawatt lasers. And actually, if you want to know more, I would refer you to the ELI webpage. And I think that in the short time that I have, I tried to show you some examples of both fundamental physics that is interesting, but also of very nice applications in medicine or security and so on, which are very useful for us. So I think that this Nobel Prize was greatly this year Nobel Prize really deserves. That Donna and Gerard really deserve to get this Nobel Prize, because what they have discovered was really for the greatest benefit to the mankind. So thank you so much for your attention.
Okay, thank you. Are there any physical limitations to the light intensity that we can achieve in the modern laser systems, or all the problems are purely economical, why we cannot get to the even higher powers by far?
So definitely the money is the problem. Also the technology, I guess. But fundamentally there is the Schwinger field limit. So with this intense laser field, 10 to the 29 volts per centimeter squared, you would be breaking QED vacuum. So as I understand it, you would basically pulling out electron-positron pairs out the vacuum. So the energy you are delivering by your petawatt laser, or no, more than petawatt, by your laser would be partially used for creating those pairs. So you would never be able to increase this intensity.
Okay, I would like to have a provocative question. Well, can you, because you mentioned some applications of laser pulses, but which of these applications really profit from having these pulses ultra short? Because, for example, for the proton therapy.
I mean, basically those applications. So those are applications. So you use your powerful, ultra high intense laser pulses as the secondary sources of this radiation. So this X-ray is absolutely not very short, right? You use your optical laser pulse. So optical means photons, energies like of the order of 1 eV, but there is many of those, and you use them to produce this X-ray radiation, right? So this is the secondary source. Of course, there are other ways to get X-rays, but each of those ways has pros and cons. And actually, the nice thing about these laser-based things is that they are very compact, yeah?
For making this progress in obtaining ultra-short laser pulses.
Ultra-short and intense.
Okay, well, for me it looks like connected.
Yeah,
But,
they are.
so is where this having ultra-short pulses really matters in applications? Or it's only for basic science when this short matters?
I mean, you need ultra-short in order to get high powers, right, and high intensities. But maybe...
That is not always the case. There are many applications in which the intensity matters. The National Ignition Facility I mentioned in my part of the lecture, this is where the energy matters. You need a lot of energy to actually ignite the fusion. But there are applications where the energy is irrelevant, intensity is what is important. Example of applications? You mean real applications?
Applications where ultra-short is really crucial.
Well, all the experiments in which you need the time resolution, right? How else would you make attoseconds?
But it's basic science. I'm asking about applications.
Well, I thought basic science is very applied or applicable, whatever you want.
Just to answering Professor Żarnecki's question, I think that if you want to follow what is going on with electrons during chemical reaction, you need these pulses which matches the time scale of what is going on with these electrons during chemical reaction. So this is one application.
So this
Of
is what...
very short pulses.
This is exactly what I showed you, right? The attoscience.
More questions? Then I want to make a comment which refers to slide maybe number 10 or whatever, if you are so kind and could go back. Yeah, the wake field. Yeah, here. So we are using it, in fact, at CERN.
In CERN,
There is an experiment which is called Awake. And it tries to accelerate electrons exactly through igniting a plasma and then creating a wave in a plasma which would carry this border there. And the wave which gives energy to the skater would go from beam pulses from superproton synchrotron, not from the highest energy LHC yet, but from SPS. And what did they achieve? They proved this is possible. And last weeks, they showed also that electrons, which energy started from MeV, got accelerated up to gigaelectronvolt, which means 8, maybe 9 orders of magnitude. And why it is so important for us, the high energy? Because we want to have very high energy electrons. They are point-like, and they may be our good, very good probes, probing the structure of other particles like a proton. And we want to have them of very high energy. However, normal acceleration is not possible since they are very light. Every light accelerated charge radiates. And after a while, a charge radiates more than acquires in acceleration. So they try somehow to bypass this, unless, of course, we may build accelerators which have 100 kilometers in diameter, or they are 100 kilometers long, or whatever. So now we are trying to find ways of accelerating electron in a different way, not by applying those standard acceleration methods. And that works actually. Unfortunately, it's not as compact as it shows here, because the present device in the awake experiment at CERN is something like 10 meters long. So it's not this, but it would fit in this room, taking all technicalities into account. And the last sentence in this long sermon is, unfortunately, it does have drawbacks as well. We not only want to have electrons of very high energy, that means very small de Broglie wavelengths, but we also want to have many of them. We call it luminosity. We want to have a dense bunch of them, dense beam. And that is not the case here. So here we may investigate ultimate energy phenomena, but with very low probability of obtaining them. Yeah.
I have two fundamental, basic questions. First one is, how can we get this smaller focus area, like diameter of less than 10 micrometer? So it will always depend on the aperture size of the lens or the nonlinear media and the focal length. So it's very important to get a lower PSF in microscopy. So that's why I'm asking.
Well, if I understood correctly, you are asking how can you get such a small focal spot?
Yes, yes.
Well, you have to start with a good quality beam. This is the necessary condition. Some of the systems we have talked about do not have good quality beams, and then cannot be focused to small spots. But if you start with a good beam, then you end up with the diffraction limitation, which means you go with a good microscope objective and you get a small spot, and
so
that's it.
It's always limited by diffraction. We can't
Yes, yes, you are limited by diffraction.
And my second question is shaping of the ultra-short pulses, does it have any effect on the intensity of the pulses, ultra-short pulses, or?
Do you want to know if the stretcher and compressor
Yes.
are lossy?
Yes, yes.
Yes, they are.
Yes.
They are. Typical throughput would be something like 50, maybe 70% in the best systems. So you always lose some energy in those.
Okay, thank you.
I would like to ask details about diffraction gratings that you have shown. Would you be able to tell what sort of pitch and what materials are used and how are they produced?
Oh, this is a very good question, actually. If you think about stretcher and compressor, then the maximum stretching or compression you can get is defined by the size of the grating. So if you really want to stretch the pulses, say, to 10 nanoseconds or maybe 15 nanoseconds, you need huge gratings about this size. This is not technically possible. So in some laboratories where they work with those with extremely strong pulses, they actually tile diffraction gratings, which means they take several of those, they put them one next to the other and align them very carefully with sub-wavelength precision to make a single huge grating about 1 meter per 1 meter. So that's technically quite challenging, actually. The gratings themselves are typically holographic, and they are either coated with metal. This is not the best solution, or they can be made with dielectric coatings. currently there's a technique that works as follows. You make a dielectric mirror on a surface of a substrate, glass substrate, and then you etch it with ion beam. You make those lines in this coating. The coating itself has basically no loss because it's made of transparent materials, and those gratings can be very efficient, 95%, for example. So that's a good technology.
Okay, thank you so much. More questions, maybe? Comments? Mm-hmm. Well, then we thank both speakers. And see you next time. Thank you.